guys, welcome back to my channel. My name is Larry, studying in Sri Venkateswara College of Engineering from the Department of CSE Data Science. Today we are going to discuss about the subject discrete mathematics. The topic what we are going to see today is homogeneous recurrence relation with constant coefficients. Introduction to recurrence relation. A recurrence relation defines a sequence where each term is expressed in terms of previous terms. These relations are essential in various fields including computer science and mathematics. Understanding their types helps in analyzing algorithms and solving problems efficiently. What is homogeneous recurrence relation? A homogeneous recurrence relation is one where all terms are defined by previous terms with no additional functions. The general form can be expressed as an is equals to c1 into an minus 1 plus c2 into an minus 2 and so on up to ck into an minus k, where c1, c2, c3 and so on up to ck are constants and an is the term being defined. Characteristic of homogeneous relations. Recurrence relations have the property that if all initial conditions are 0, all subsequent terms will also be 0. They are linear in nature, meaning they adhere to the principles of superposition and homogeneity. These relations often arise in the analysis of linear system and dynamic programming. Constant coefficients is explained as imply that the multipliers of the previous term do not change with n. This characteristic simplifies the process of solving these types of relations. In contrast, non-constant coefficients would lead to a more complex analysis and solutions. General form and examples. The general form of kth order homogeneous recurrence relation is an is equals to c1 into an minus 1 plus c2 into an minus 2 plus and so on up to ck into an minus k. An example is the Fibonacci sequence where an is equals to an minus 1 plus an minus 2 with initial conditions. Understanding specific examples helps in grasping the concept of these relations better. Solving homogeneous recurrences. The first step in solving a homogeneous recurrence is to find the characteristic equation. The characteristic equation is derived by replacing an with r power n, leading to a polynomial. Roots of the characteristic equation help determine the form of general solutions. Characteristic equation and roots. Characteristic equation for a kth order relation is typically a polynomial of degree k. The roots can be real or complex and their natural effects the solution form. Distinct roots leads to a specific solution form while repeat roots introduce additional terms. General solution structure. The general solution of a homogeneous recurrence relation is a linear combination of terms derived from the roots. For distinct roots, the solution is of the form an is equals to c1 into r1 to the power n plus c2 into r2 to the power n plus so on up to ck into rk to the power n. For repeated roots, the solution incorporates polynomial terms multiplied by the exponential terms. Initial condition. Initial conditions are crucial for determining the specific solution from the general forms. They provide the necessary values to solve for the constant in the general solution. Without initial condition, the solution remains in general form and lacks specificity. Application of homogeneous recurrence. Homogeneous recurrence relations are widely used in algorithms analysis, especially in dynamic programming. They also appear in combinatorial problems such as counting paths or configurations. Understanding these relations allows for efficient algorithm design and problem solving strategies. Thank you guys for watching this video.